Welcome back. In this segment, we are going to look at another key property of the finite element method, and this is called the best approximation property. It draws in a very important way from the main result that we had in the segment preceding this one, and that result is the consistency of the finite element method. Okay, so let's get started here. We are going to look at, in this segment, the best approximation property. Okay, in order to build up to this result, let's consider the following, right? Let us denote, as we've been doing so far, let UH, which we recall belongs to SH, be the finite element solution. Okay, all right. And let WH, as we've been doing also, belongs to VH, be a weighting function. Okay, and note that I'm saying it is a weighting function, and the idea is that we are going to consider any weighting function living in VH. Okay, now I'm going to introduce a third field that we have not previously considered. Okay, I'm going to denote this as capital UH. It too belongs to SH. Okay, and however, it is not the finite element solution. Okay, so what does this mean? This means that when we say that UH belongs to SH, we are recalling that SH finally consists of functions, right? Since capital UH is meant to denote a general member of SH, which is typically different from the finite element solution, right? What that means is that UH belongs to H1 on omega, and UH satisfies the Dirichlet condition, right? The Dirichlet boundary condition. Okay, and let us suppose that we are working with the Dirichlet-Neumann problem, right? And you know how this would work if we were doing the pure Dirichlet problem. We would have the other boundary condition also in there. Okay, so this is UH. All right. If we have this, let us note that, okay, note the following. Okay, note that any UH, okay, can be written as the finite element solution, okay, plus WH. Okay, why is this? Note that as I made a point above, WH is any weighting function. UH is a very specific member of SH. It is in fact the finite element solution. All right. Also note that UH belongs to H1 and so does WH. Okay. Therefore, their sum also belongs to H1. We haven't quite proven it, but you can probably see why that works out. It does indeed work out rigorously. Therefore, when we add UH and WH, we recover functions which live in H1, which remember, or which we recall from just out here, is also a property of UH. Okay, so adding little UH and WH maintains that property of capital UH. What about satisfaction of the Dirichlet boundary condition which capital UH has? Well, remember that since little UH is the finite element solution, it does satisfy the Dirichlet boundary condition. What about WH? Does WH not mess up that result? It doesn't, because WH is 0 on the Dirichlet boundary. Okay? Okay? So note that when we write UH in this form, capital UH in this form, it does indeed satisfy all the requirements we have for this new set of functions, capital UH. Okay? So let me just state that UH equals little UH plus WH, right, where little UH is a finite element solution and WH is any weighting function. Okay? This does indeed belong to H1, right? And I will just write and satisfies the Dirichlet boundary condition. Okay? In what we are going to do today, the main result of this segment, we will use this result in an important manner. Okay, so with that in place, let me state the main result of this segment. It's a theorem, really. Right? And that theorem is the following. If we consider the energy norm of the error, and here I'm writing the energy norm using abstract notation. In one of the segments preceding this one, we demonstrated that with abstract notation for the bilinear form as we had defined it, we do indeed get the energy norm of the error if we write it in this form. All right, so the theorem is that the energy norm of the error is bounded from above by the energy norm of what you may also consider the error, except it is capital UH, this new field that we've introduced, minus U Okay, this is the result that we are going to prove. Why is it of interest? Note that E, the error, is the finite element solution, that's little UH minus U. Okay, so what we are saying here in this theorem statement is that the energy norm of the error, okay, is such that such that the finite element method has picked a member of SH, okay, to be the finite element solution, which gives us the lowest energy of any possible other member of SH. Okay, right? So let me state give you a plain English statement for the relevance of this theorem. Okay, so what we are saying here is that the finite element solution minimizes the energy norm of UH minus U over all members UH belonging to SH. Okay, the space SH consists of a number of functions. Okay, one of them is the finite element solution, that finite element solution is that member of SH that minimizes the energy norm of the difference between that function and the exact solution. Okay? In this sense, with the energy norm as a measure, the finite element method picks the best possible approximation among all members of SH. Okay? And this is why we call this segment the best approximation property, and in fact this theorem is called the best, the statement that we have here represents the best approximation property. Okay? And this holds for all UH belonging to SH. Okay? All right, you're going to set about proving it. To prove it, let us first consider the energy norm of a slightly different function. I want to consider the energy norm of E plus WH. Right? Now we know how to expand this out. Right? We get a result which works just like the expansion of a perfect square. Okay? It is that this is equal to A, E comma E plus 2 times A. Well, let me write it out more explicitly. This is a subsequent step. Plus A E comma WH plus A WH comma E plus A WH comma WH. All right, and this comes about just from the expansion. If you were to go back and look at what this abstract notation actually represents for the energy norm, that using the fact that it is bilinear in its 2 arguments, right? These being the 2 arguments, you will get this result, right? It's just like the expansion of a perfect square. And then one recognizes that because the bilinear form also is symmetric, right? We note, what do we get from the result that the bilinear form is symmetric? Right, we see that these 2 terms, right, are equal. Okay, so that lets us then write it out as energy norm of E plus the bilinear form A. Let me write it as WH comma E. Okay, recognizing that the second and third terms in the line above are equal, plus A of WH comma WH. All right? Okay. Stare at this now and try to recall whether we can say something special about this term. Right? Indeed we can. In the previous segment, we demonstrated that this term is equal to 0. And this term is equal to 0 is a result that we've termed consistency of the finite element method. Right? It is the result that it comes from consistency of the finite element method, and consistency of the finite element method itself, you recall, is the fact that the finite dimensional weak form admits the exact solution as a solution, right? It recognizes the exact solution. Okay, so what this says then is that what we started out with at the top of this slide is A of E comma E plus A of WH comma WH. Now, each of the 2 terms on the right-hand side is an energy norm. Right? The first is the energy norm of the error. The second is the energy norm of the weighting function. There is a property of norms, right? A fundamental property of a norm. right? Almost the definition of a norm. It is that each of these has to be greater than or equal to 0. And you can go back and check from our definition of what the energy norm is that indeed this holds. Okay? All right. But if this is the case, what this implies for us is that, let me now just pull down the term from the left-hand side here. A of E plus WH, comma E plus WH equals this. Okay, what this implies for us is that A of E comma E, I'm just writing the energy norm of the error, right, this term. Okay, what it implies for us is that, well, let me ask you, how is this term related to A of E plus WH? E plus WH. What's the relation here? Right, it is lesser than or equal to it. Okay? Right, simply because the sum of two non-zero terms on the right-hand side is equal to the term on the left-hand side. So if we get rid of one of those non-zero terms, well, what remains must be lesser than or equal to what we had on the left-hand side, and I've just flipped around their positions. Okay? And now we're getting somewhere. In order to proceed, let me go to the next slide. I'm going to rewrite this term differently. Okay, the term on the right-hand side. Note that A E plus WH comma E plus WH is equal to A. Now the error. I'm going to rewrite the error in terms of the finite element solution and the exact solution. The way we defined the error was simply the finite element solution little UH minus the exact solution U. And we have WH there. And the same in the second slot, UH minus U plus WH. Okay? But now I can recombine this, right? I note that when I get U and WH, UH and WH, this is from the result we proved at the beginning of the segment, just capital UH, right? The function that we introduced, which we identified as being any arbitrary function in SH. Okay? That minus U, comma, same thing on the left hand for the second slot. All right. Now we put this together with what we had at the bottom of the previous slide, right, which is this result at the bottom of the slide. So combining with the inequality above, right, the inequality that we came upon just a few minutes ago, we see that that inequality, which is A of E comma E, is lesser than or equal to this term. Okay, well, that means it's also it's lesser than or equal to UH minus U, comma UH minus U. This is what we set out to prove. Okay, we're done. What we've done here is prove the best approximation property, right? And I'll restate the significance of this result. It says that the other way to write this is instead of you expand out the error, right, which is UH minus U. Okay, so the energy norm of the error, where the error is defined as the difference between the finite element solution and the exact solution, is bounded from above, right, by the energy norm of any other function living in SH, right? Any other function, right? For all UH belonging to SH. But little UH, the finite element solution, also belongs to SH. So what the finite element method does is that it picks for us the solution, as the finite element solution, that member of SH that minimizes the energy norm, right, of the difference between the function and the exact solution. So it's in this sense that we have this best approximation property. Okay, so re-emphasize that. Let me just state that this is what we mean by the best approximation property. Okay, and just remember in all of this that what we have as little UH is indeed the finite element solution. All right. So the finite element method does a very efficient job. Once we pick our space SH, does a very efficient job of choosing that member of SH that minimizes the norm of this difference. Okay, and says that, well, that is your finite element solution. Okay, all right, good. We'll end this segment here.